It looks like we're live. Hello, everybody, and welcome back to another Hangout. Today, I have with me Part-Time Vegan. So, hello, Part-Time Vegan.
Hello, hello.
All right. So, you're a flat earther, right?
Yeah.
Okay. One thing that I really like asking flat earthers is, what's your best point? Like, if you had one argument that you would have to base your reputation on, what would that be to convince me that the Earth is flat?
I think we're going to be intellectually honest here. The Earth appears flat. You know, we experience a flat Earth, and I guess flat Earthers, we believe in our senses, and round Earthers, they believe in models. So I guess that's my point.
Well, I certainly agree that from ground level the Earth appears to be flat, but when we use actual measurements, not well from ground level and from higher altitudes, we see that it isn't. So the thing is
we
that
see curvature from high altitudes.
Yes, we do. I mean, we can measure the angle in which the horizon drops below eye level, even at cruising altitudes of aircraft. At 10,000 meters altitude, the horizon will appear approximately 3.3 degrees lower than eye level.
So are you just defining that as curvature? Because I don't necessarily agree with that interpretation.
Yeah, I mean, it's what is expected from a spherical Earth, and we observe that.
Right, that's a model. So you believe in models, not your experience.
Well, when we can measure it, it is an experience, right?
No, you just believe in a model and interpreting what you see based off that model. So, yeah.
No. Well, we're comparing two models here. You're saying that you think that the flat Earth model is correct. I'm saying that the spherical Earth model is correct.
The thing is, flat Earth, we don't even, to be honest, we don't even actually have a model. In fact, I would say that there's a lot of things that we don't understand about the stars. And like, to me, just the fact that, you believe that the sun is 400 times bigger than the moon, like, we can't really, we don't experience that. I mean, just by appearance, it looks like they're the same size.
Let's go back one step first. You said again that you experienced the Earth to be flat, right?
Right.
Okay, so you're saying that well, when you're saying that the Earth is flat, you're automatically saying that you at that point, when you're saying that, you're starting to run a model in your brain, like I think the Earth is flat, and the observations that I do are in agreement with that, right? That's what automatically happens.
Yeah, when I look at the ocean environment, I'm in a plane, it looks flat.
Yeah, only the fact that it doesn't.
So it does look curved to you? Did you not just say it appears flat?
From a plane scene, yeah, it does appear curved because
so you can see curvature from the plane.
Yeah, we can measure the dip of the horizon.
No. Is that? But you're defining that as curvature.
It's the result of curvature.
I don't agree with that Well, that's based on your model. So you're believing your model of your senses. So that's so here's the thing. I think it's almost pointless to argue because fundamentally we think differently. I believe my senses. You believe in models. So you're going to keep asserting that it's curvature, and I'm saying I don't agree with that interpretation.
That's not correct. First of all, we have no reason to trust our senses alone.
Wait, hold on.
Wait,
You can't make that assertion.
Hey,
because it's meaningless. How can we have a conversation if we can't trust our senses? It's meaningless.
It's because you interrupted me and I couldn't finish my sentence.
Okay.
Simple. When we have better measurement tools to actually use, when we have, for example, theodolites, which can determine angles that are so small that we can't see them with our eyes, we have to depend on the best instruments that we have. And all of them are pointing towards the direction of the Earth being spherical.
Are you done with your sentence?
Yes.
I disagree.
Why?
I just disagree with your first premise that we can't trust our senses. If you say that, then this conversation is meaningless. It's literally meaningless.
Well, what I'm saying is that when we have the choice between using our eyes to determine an angle, for example, or a distance, why should we use these when we have tools that are better?
So let me paint you an analogy so we can get a better understanding of what's going on here.
All right.
So I don't think you're necessarily attacking our senses. I think you're attacking our perspective. So let's say somebody's wearing camouflage, right?
All right.
My senses detects that there's something there. Okay. Now, from my perspective, I might think it's actually a tree, but it's really a person. My senses haven't failed me. My perspective has failed me, because if I saw it from maybe a different perspective, I would say, oh, this is obviously somebody wearing camouflage. So I think you're not necessarily attacking senses. We can't trust our senses. You're attacking our perspective, as in how we see the world. Is that more accurate?
No, that's not correct. In your analogy, when you are using your senses, the senses that you have, you are not able to determine every evidence of the existence of that camouflage person. For example,
I'm seeing it. I'm still seeing it. How am I not experiencing it if I'm seeing it?
Well, you're saying you could mix them up with a tree, right?
Yeah, that's perspective. That's not what I'm seeing is still there. It's very real what I'm seeing.
Yes, but I'm saying you can use tools to determine more precisely what this actually is, what you're looking at.
What do the tools do?
Hey, for example, an infrared camera that could determine whether that in front of you is a person or a tree.
Okay, so what are the tools doing? They're changing our perspective. Our senses are still real. Our senses are, we can trust our senses, but the tools we use change our perspective. They give us a different look on reality.
No, they don't. They just give us more.
How do they not? So you're saying tools do not change our view of reality? They
give us additional data.
Exactly. So it's changing our perspective, correct?
First of all, define perspective.
So senses is what you see, and perspective is how you see it.
How you see it by what methodology?
What?
Well, for example, you're saying our senses are, for example, what we see, right?
Right.
Well, when you're talking about perspective, are you talking like from which position we are seeing something? Like a local thing? A geometrical thing?
It could be geometrical, yeah.
Yeah, but in your example, it isn't.
How's it not?
Well, you're saying that using another device, like, for example, I'm saying using in your example an infrared camera would change my perspective. How would replacing your eyes with an IR camera change my perspective? This is not a geometrical thing.
So in your example about, I said it could be geometrical, but in your analogy, when you gave me the infrared camera, that's like sensing, obviously infrared. So isn't that like sensing heat or?
Yeah, first of all, there are various different wavelengths of infrared. Some are irradiated by heat and some aren't.
Right.
But yeah, you would practically gain more information of the photons that are coming out of that object. And second of all, it was your analogy. You came up with that, not mine.
Right. So, but in order to even interpret those results, we have to use our senses, correct?
No.
Oh, so we can just see it. We can just interpret it blindfolded?
No, we have to know how the instruments work.
Right. So, but we have to use our senses to do that, correct?
Yeah. Well, then in then in an ultimate sense, we can only rely on our senses. Yes.
Okay. So what you said was factually wrong when you said we can't trust our senses.
Well, how do you know that your senses are doing the right thing right now? How do you know that you're not connected to?
Well, yeah. Well, if you're going to make that argument, this is a pointless conversation.
Yeah, I agree with you, and that's why.
So why would you make that argument?
To show you that we have to agree first that that the reality around us is actually real.
Well, see, your first assertion, one of your first assertions were we can't trust our senses. And I just demonstrated how that's factually wrong. Even if we're using an instrument, we still have to use our senses to interpret the data.
Yes, but when we compare our abilities of our senses to actually gain information, the instruments that we can use are more precise.
So you're saying that instruments can help our senses. I agree with you. I agree with you.
For example, they can help our senses, yes, and they can completely replace them. And second of all,
no, they can't replace them because we're still subject to.
Of course they can. Of course they can. You can see you can see a person, or you can get the information, or you can see the photons of a person coming from that person, run it through an IR camera, and then find out where that is.
And how did you interpret that data?
There are various methodologies. I mean, you could get
no. How did you interpret that data?
By looking at it.
By looking at it. So you're using your senses.
Yeah, as I said, in an ultimate sense, yes.
It can't replace it, but it can help us get a better perspective of what we're looking at.
Because first of all, don't use the word perspective. This is so imprecise. I wouldn't do this. But the reason we're using this is we can't rely on our senses being precise, and we know that our senses can be fooled. Instruments can't.
If you're aware that your senses can be fooled, then how are your senses fooled?
For example, in optical illusions.
But if you're aware of it, if you can sense that you're being fooled, then how are you being fooled?
I can compare it to other input methods. For example, when I have one of these typical optical illusions, like do you know the one where there are two figurines that are standing in different positions on a 2D surface, and there are diagonal lines that give the appearance of the figurine standing in a hallway.
Right.
And one of them appears larger than the other one.
Right.
All right. You can measure that one of them is larger than the other one, or that they're identical, by using a ruler.
So basically, you're telling me that you can be aware, using your senses, you can be aware that your senses can be fooled. Therefore, yes. You can, but you're still using what?
You're using other senses, or at least
you still use your senses. So therefore, you can still trust your senses.
This is a way of cross-confirming what is actually the case. That's why you shouldn't rely on one input method, and that's why I'm saying use, for example, theodolites when you're talking about angles.
And whatever type of measurements and instruments you're going to use, we're still going to be subject to our senses. Even in cases of optical illusions, the fact that we're aware that we are being tricked, we're still using our senses to determine that.
All right, let's do one example, okay? There are two lines next to each other.
Right.
And to you, they appear parallel.
Right.
Okay? Now, with a set of theodolites, with one theodolite, actually, you can determine how parallel they are. Okay, and it turns out they are just 0.0012 degrees or so off. Like, it's minuscule. You can't see this with your eye. Okay?
You can see it with your eye.
No, you cannot see this.
But aren't you looking through the theodolite with your eye?
Yeah, that's the point that I'm making.
So you can't see it with your eye.
No, you can't. You need the theodolite as an instrument. That's what I'm saying.
Right. And what are you using with that theodolite? Your eye?
Not necessarily.
Oh, so you can use it blindfolded?
You could run it through a computer and give out the information via audio.
And you would use your ears to hear that, huh?
Yeah, I mean that. As I already said, in the end, there always has to be an input into the person. I mean, the computer could do this as well, obviously, and we would get the same information from it.
Right. But in any sense, again, you have to use your senses to interpret the data, regardless.
No.
Okay, so you're telling me we can interpret data without using our senses?
Well,
how is that possible?
I already told you. The data we get can be put into you by different methodologies. And yes, that's
put into you, but hey, interpret that using your senses.
Let me make my goddamn point for once, okay?
Oh, go ahead.
All right. As said, finally, yes, the information must get into your brain somehow. And the only way that we have is, per definition, the senses. But
there we go.
The information doesn't have to come in like optically, for example. And we can rely that the theodolite that we're using, for example, is much more accurate than our eyesight. That doesn't mean we use our eyes to determine the angle between the two. No, we use the theodolite. And the data that it's putting out, well, we have to read it in some way, but we are not using our eyes to directly gain the information of the information between the angles. We don't get that. No, we use the theodolite.
Yeah, well, you basically just said what I wanted you to say. It still takes some type of input to your brain, which uses your senses. So therefore, everything you're saying basically correlates to what I'm saying. So I have no issue with what you're saying. All
right. So back to the actual evidence, okay?
Okay.
All right. So again, we're discussing here, is the flat or is it spherical? And from asking the questions and from taking from thinking about the implications of the two different possibilities, we can actually determine what's more likely by comparing it to actual evidence. All right? And pretty much everything that we have, actually everything that we have, appears or shows that the Earth is spherical. We could talk about, for example, the position of the pole stars. We could talk about the horizon dropping below eye level. We could talk about theodolite data, actual theodolite data. Take your pick.
Well, like I said, it's kind of pointless, isn't it? Because we just fundamentally disagree.
No.
You're basing your interpretation of reality off a model, and I believe my senses. I don't believe your model. So
I already told you why it's not true. Do you agree that at 45 degrees latitude, the pole star is at 45 degrees over your horizon?
At 45 degrees latitude, say that again.
At 45 degrees latitude, so you're at 45 degrees north, right?
Right.
The pole star will be at 45 degrees over the horizon.
Sure.
All right, and at, for example, 90 degrees latitude, meaning you are at the North Pole, then the pole star will be at 90 degrees over the horizon. And at 30 degrees latitude, the pole star will be 30 degrees over the horizon. This is something that is not possible on a flat surface.
Oh, it just depends on how the stars work, honestly.
No, it doesn't.
Oh, it doesn't.
I mean, you have to come up with a geometrical explanation that explains this. And
well, yeah. Well, just because I don't have an explanation
already work on spheres.
Well, just because I can't provide an explanation doesn't mean there isn't one.
Yes, but I actually can provide an explanation. That's the difference.
So you understand the stars, huh?
Yes.
Okay. Well, I mean, you believe that, but is it possible you could be wrong about your understanding?
About the geometry of the stars? No.
Oh, it's not possible you could be wrong about the. No, I'm saying about just the properties of the stars in general. Is it possible you could be wrong about it?
You mean how the stars themselves are formed, or what? Or what they actually are?
Yeah, about what they actually are. Is it possible you could be wrong about that?
In terms of astronomy, yes. But I still
well,
can.
there you go. So there you go.
But I can still show at which positions they are, and I can predict the positions where the stars will be depending on your position on the planet. This is something that flat earthers cannot do.
Well, not necessarily, because people before there was even a globe model were predicting the placement of the stars, so that's irrelevant.
That is not correct.
How is that not correct?
Because you can't do it. When
they
you're
might. Oh, so you're saying that people, so before the globe model, nobody knew when the stars were going to be where they're at, huh? Nobody knew that?
They couldn't predict it. At least not.
How are they making calendars and not all the other stuff?
Calendars can be done using the moon and the sun.
Right. It also can be used using the stars. I believe the Chinese calendar actually shows the constellations each month by just tracking the stars.
Yeah, I mean, that's possible, but you would have to have a timer for that as well.
So there you go.
Obviously.
Well, there you go.
But again, how do you answer to my question that you can predict the positions of the stars, for example, the North Star, only knowing your latitude? This is not possible on a flat Earth.
So you're saying
you will always run into geometric problems.
Yeah, well, it just depends on our understanding of what stars are.
All right. Can you, when I tell you now the position of a person on the planet, can you use a flat Earth model or flat Earth knowledge to determine where the stars are?
So your argument is say what?
I asked you a question. Let's say you know where you are on the planet, okay?
Okay.
And you're in a building, and you know it's night, and you know that the sky is clear. When you go outside, can you determine where the stars will be? Which individuals
I'm not an astronomer, so no, I can't.
Yeah, but we actually can.
So what's your point?
The point is that we have a model that works, and you do not.
Right. So yeah. Well, I'll admit that you have a model, but that doesn't mean it pertains to reality. Just because something explains reality doesn't mean it pertains to reality.
Actually, yes, it does.
No, that's not true.
Yes.
No, that's not true at all.
Yes, the model we have is predicting every single appearance in the sky to a very close degree of correctness.
So I could mathematically model a unicorn that's always behind you, therefore you never see it. And it'll explain what you're seeing in reality because you'll obviously never see the unicorn because I mathematically described why it's always behind you, but that doesn't mean that unicorn exists. So just because a model,
you realize that I can, sorry.
Just because a model explains reality doesn't mean it pertains to reality.
This is not correct, because I can use an instrument to determine if that unicorn is actually there, and it's called the camera.
Okay. Well, I'll just add that to the equation. It's also above that. It also can disappear with that instrument.
Then I use a different instrument.
I'll just add that to the equation, and I'll just keep on explaining it away.
All right. Then at some point you will have something that cannot be detected by default and is therefore useless.
Well, what do you know? That's what we have with the flat Earth. I mean, with the round Earth model.
That the flat Earth is useless. Nice.
No, that was clearly a mistalk. Now I'm saying that the globe Earth is useless because every time like we see further than what we should see, it's like, oh well, it's obviously refraction. It's obviously X. It's obviously Y. It's obviously Z.
Well, you know that we have a very good explanation for refraction, what is actually causing it, and that we can predict it as well, right? We have a formula where you plug in the atmospheric conditions, and it will tell you how big refraction actually is.
Well, and if it doesn't conform to that, then you'll just change the refraction index and say, oh,
no, that's not correct.
Well,
that's not correct. Well, if we are 100% sure about the atmospheric conditions, then we will.
Well, that's just reverse engineering the results, isn't it?
No, it isn't.
Oh well, yeah, it is. Because no. Did you keep up with the? Did you keep up with the Isle of Man debate on Nathan's channel?
Yes, of course. I've been in his chat today, and I think yesterday as well.
So basically, they just reversed calculated how. It was non-standard refraction, or.
Yeah, but they don't seem to understand how we actually get the formula for non-standard refraction. We derive it from a few things. For example, the ideal gas law and Snell's law. We can derive the calculation for non-standard refraction only using known physics. Well, it's hard to do, but it's possible.
Right. Well. Anyways, that's literally just based on your model. So, I guess if you could prove your model, that'd be awesome.
Yeah, we already did. That's why we continue using it every single day, and it yields accurate results, right?
Okay, so hold on. So did you have an issue with my unicorn example?
Did I have an issue with the unicorn example?
Yeah.
No. What I'm saying is,
you do understand that just because. Okay, hold on. Let me just finish this. So you do understand that just because something explains reality doesn't mean it pertains to reality. Do you agree with that?
No, because the unicorn actually doesn't explain anything.
How?
What is its practical application?
Fooling you. That's its practical application.
No. Like,
why not? Why not? Okay, hold on. You said no, but why not?
What can unicorn theory tell you about the universe?
Just because it tells you that you can easily be fooled.
Again, that's not useful.
Well, practical application. Hold on. You said that's not useful. That's just your opinion. That's useful to me.
No, for example, a useful application of the sphere model that we have is to actually predict when solar eclipses will occur. What can your unicorn model do in that regard? What can it do that? What can your unicorn model predict that about future events?
Okay, so are you saying that in order for something to exist, it must have a prerequisite idea that it must be useful to you?
No, in order for a theory, a scientific theory to be good, to be useful, it must be able to predict future events.
Does it have to be useful?
Yes.
To exist, though. Hold on. Does it have to be useful to exist?
Useful only in the sense that it has to be able to predict stuff.
Oh, so in order for something to exist, it has to be able to predict stuff.
No, that's not what I'm saying. I'm saying for a theory, a scientific theory, to be valid, a good indication for that is when it's able to predict stuff.
Okay, I'm not talking about scientific theory. I'm just talking about pure ontology. This is just pure ontology. Can a unicorn exist that's always behind you? Is that possible? Whether scientific or not, is that possible?
Yes. It's possible.
Okay, then. Okay,
No. Yeah, I say it can exist, but we can rule it out if it does.
So, I can describe a unicorn that's always behind you and mathematically explain how it's always behind you. But just because I can explain that reality doesn't mean it pertains to reality. Do you agree with that?
Yes, but you can.
Okay, there we go then.
Whoa,
there we go.
Hey, you interrupted me again mid-sentence. I'm sorry. But if you don't let me finish my sentences, there's no point in talking to you.
Okay, go ahead.
As said, it's possible that one exists, but we can rule it out. And this is what has been done with flat Earth. We ruled it out by doing more observations. And when you're not saying that, yeah, you can describe it in a different way, so that like looking at it or setting up a camera or so also wouldn't be able to describe it, then yeah, that's also what's happening with flat Earth, because you're running so deep into the rabbit hole that at some point you can just dismiss anything without giving any reason. That's what's happening.
Okay, so Gio, you actually seem like an honest, nice guy. So I'm actually just gonna go ahead. I'll go ahead and play the game, but because you already said what I wanted you to say. Just because something explains reality doesn't mean it pertains to reality. You literally agree with me on that point. So I'll go ahead and play this game of we can talk about whatever you want to talk about, because that was basically
let's actually talk evidence, okay?
All right, let's go.
All right, so let's start with the stars, okay? Let me just set up my screen so we can check. No, not Celestia, wrong program. I need Stellarium. Where is it? There it is. Oh, it's making my computer lag as fuck, Stellarium. All right, can you see my screen?
Hold on, let me click on your screen. Okay, yes. All
right, let's just add in the equatorial coordinate grid and the azimuthal coordinate grid. I'm now at, where am I? Location. I'm at...
what program is this?
It's called Stellarium.
All right, cool. Let's go.
So right now we're at 51 degrees north and 9 degrees east. Okay.
50 degrees north, 90 degrees. Okay, so I guess that red arrow points where you guys are at. Okay, gotcha.
Basically I'm somewhere here in Central Europe. This is actually not my location. No idea where this is. I think this just picks the position randomly.
Okay.
Let's take a look at the pole star. Here's the northern celestial pole. And we already said we are at 51 degrees north. And if you actually take a look at this green coordinate grid that you see, you will see that the center of the coordinate system is at 51 degrees in a little bit. Okay?
Hold on. 51 degrees. Why aren't there numbers on your thing? Oh, wait, I see it. It's at the bottom.
On the left side there, 51 degrees.
Okay, gotcha.
Okay, so it's a little bit more than 51 degrees. Now let's actually compare this to our location. It's pretty much at 51 degrees. Okay?
Okay.
So let's just randomly go to another location in the northern hemisphere. Now we're somewhere in Scandinavia. I don't know where exactly. Now we're at 65 degrees north. So based on the sphere model, I can now make a prediction where the northern celestial pole is going to be. It's going to be at 65 degrees over your head. So let's see. Here's a 65-degree line, and it's higher than 65, about 65.15 degrees. There it is, right there. Now, again, this angle between, so this is the angle, the azimuthal angle from basically the horizon is defined as 0, and directly over your head is 90 degrees. And again, this is at 65 degrees. We can do this with pretty much any position in the northern hemisphere. For example, let's go to pretty close to the equator. We are now at 15 degrees north. And as you can see, the center of the northern celestial sky is a little bit higher than 15 degrees. This does not work on a flat Earth. This only works on a spherical Earth. It's a direct consequence of the Earth being spherical.
I wouldn't say it doesn't work on a flat Earth. I would say it hasn't been explained on a flat Earth. I think that's more honest to say. And if you're going to say it hasn't been explained on a flat Earth, okay, well.
No, this is literally impossible.
Okay, I mean, well, like I said, but hold on. Is that not predicated on how you understand the stars?
No.
Oh, so it's not predicated on how you understand the stars.
No, I mean,
for every single. That's dishonest.
for every single location on the planet, we can actually measure this, and this turns out always to be correct. So yeah, we can assume that the light rays coming from the stars are roughly parallel. That's something we can assume. And so from this, we can actually derive the circumference or the radius of the planet.
So Gio, if you're going to say this has not been explained on flat Earth, I agree with you. If you're going to assert it's impossible, I disagree with you, because how do you know you're taking into account all the properties of the stars?
Well, first of all, you're the one who's. First of all,
you made the assertion, so the burden of proof is on you.
I'm trying to explain this to you. First of all, in order to show that something is possible, you actually have to show first that there's a possibility that it's possible. If you know what I mean, you have to come out with an idea where actually to start from, to derive a model that shows the same behavior, but is starting from a flat Earth. And this is something that hasn't happened.
All right, I agree. Okay, in that sense, I agree with you. But like I said, you made the assertion, so the burden of proof is on you. Now, if you say flat Earth hasn't explained this, okay, I agree with you.
All right, so you're saying the burden of proof is on me to actually prove that it's impossible?
Yes.
All right, then I would say that first of all, you haven't met any standards. You haven't shown anything to be possible at all. Then I can just dismiss this without actually proving it. What can be asserted without evidence can be dismissed without evidence, right?
Okay, so basically your assertion is baseless, right?
No, that's not what I'm saying. I'm saying you haven't shown any probability that this is possible on a flat Earth. Therefore, I'm justified in dismissing it.
Right. Okay. So you're dismissing it. That's separate from what your assertion is. Your assertion is it's impossible on a flat Earth. You made the assertion.
Yes, because you haven't shown any possibility for it.
Did you prove the assertion?
What?
Did you prove your assertion?
I already told you why I can make the assertion without proving it in this case. Because what can be asserted without evidence, which is what you're doing, can be dismissed without evidence.
Okay, so you can dismiss it all you want, but that assertion that you're saying is factually incorrect.
No. Again,
then prove it.
No. Stop again. Your assertion that you say this might be explainable on a flat Earth, this one is baseless. And since it is baseless, I'm justified in dismissing it. That's my point.
Yes. Okay, Gio, I have no issue with you dismissing it. I have an issue with the assertion you're making. You asserted that it's impossible on a flat Earth, so prove it.
I already told you I don't have to. You have to prove that there's a possibility first.
Okay, so will you agree that you have not proven your assertion?
No.
So you did prove your assertion?
Yes.
How did you prove your assertion?
Wait. Okay, then. We're talking past each other. You understand I'm justified in not accepting your assertion because it's baseless, right?
Listen, yeah, you don't have to accept. You can dismiss it. I agree with you.
All right. Therefore, you haven't shown any possibility for this to be the case.
Who made the assertion, me or you?
You.
No, you made the assertion. You said you asserted it's impossible on a flat Earth. I didn't assert anything.
No. We have to go one step back. I think that's where our misunderstanding lies.
Okay.
You said it might be possible on a flat Earth.
No, I asked you, how do you? I said, is your critique? Okay, listen. This is what I said. So let me interject. I said, is your critique based on or predicated upon your understanding of the stars? And you said, I think you said no. You might have said yes. If you said yes, then I'll ask you, how do you know that your understanding of the stars is correct? And this is the thing. See, it's more intellectually honest to say this has not been explained on a flat Earth than to say it's impossible on a flat Earth. Because once you make that assertion that if you make the assertion it's not been explained on a flat Earth, well, I can't argue with that. That's true.
No.
Okay, we haven't explained it. But
it's a geometrical fact that this is not working on a flat Earth.
It's a geometrical fact. Well,
yeah,
it's a geometric fact. Hold on. Let me think about that. It's a geometric fact. Well, geometry depends on appearance too, so you can't even say that. You can just say it's not been explained on the. Oh, it doesn't. Wait.
No, I mean we can measure. We can at least from ground observations estimate the distance to the different stars. We know that the light rays are parallel enough to assume that they are so parallel that we can assume them to be infinitely far away.
Is geometry dictated by appearance? Yes or no?
Is geometry dictated by appearance? Geometry itself is a piece of mathematics. So I would say no. Is the geometry, or are the angles of the individual positions, or the angles that you're actually measuring, dependent on where your points are? Yes.
So it is. So no. It does. Okay. So geometry is partially dictated by appearance. Would you agree with that?
No, geometry itself isn't.
So you're telling me I can do geometry without knowing the appearance of anything?
Yeah, I mean, you can know the rules of geometry, right? You're aware of it, right?
Well, you have to see the object to do geometry on it, correct?
We're not. First of all, you're talking about geometry in general.
No, I'm talking about doing geometry. In order to do geometry, I have to know the appearance. Like I have to see the object, correct?
If you want to do actual measurements, yes.
Okay, so it is partially dictated by appearance. So the only assertion,
measurements are, but geometry itself isn't.
The only assertion you can make here is that this has not been explained on the flat Earth. That's the only assertion you can make.
No, because every single model that, or every single suggestion from flat earthers that we find turns out to be false. I think there's even a good argument to say that falls. Hey! I think there's even a good point to make that since all the propositions that we've heard from flat earthers turned out to be completely false, it's a good point to make that, yeah, it's not possible. No. Because people have tried and they failed.
No. Well, so Gia, you do understand that just because there's not a current explanation doesn't mean there's not an explanation, right?
Yes, that's correct.
All right. So basically the only assertion you can make here is that it has not been explained on flat Earth.
And no, what I can say is people try to explain it on flat surfaces.
I don't get why you guys are so...
What the heck? Why are you interrupting me again? Why are you? What I'm saying is people have tried to explain this on flat surfaces, and repeatedly they have not shown that they can produce the results that we actually observe. Therefore, it's justifiable to think that, yeah, it's not possible because people have tried. People have tried again and again, and all the results turned up to be false.
So can I talk now?
Yeah.
So what you just said is people have tried to explain it and have yet to explain it. Therefore, the assertion to be made is this is yet to be explained on a flat Earth. It's just that simple. I don't get why you can't just say that. Why do we have to take that next step and say, oh, it's impossible? Just say it hasn't been explained. I mean, if it hasn't been explained, then it warrants an explanation. Then we have to solve it. Okay, I agree with you. But don't say it's impossible because that's just being intellectually dishonest.
That's not correct. I'm saying it's impossible because, again, people have tried.
It's impossible.
Hey, people have tried again and again, and they haven't come up with anything. So what's more likely, that they will come up with something, or that the other alternative hypothesis is correct, that is currently working, and that has been working for a few millennia? Which one is more likely?
Gio, you just agreed.
Which one is more likely?
Okay, ask your question again. I'll go ahead and answer it.
All right. So I'm saying people have tried again and again to find flat Earth models that can explain this.
Right.
All right. Which is more likely, that even though people have failed doing this, this hypothesis is correct, or that the other one is correct, namely the Earth being spherical, which has produced accurate results for the last 2,000 or 3,000 years? What is more likely?
I don't agree with that dichotomy.
This is not a dichotomy. I'm just saying.
No. You're telling me either X or Y.
I mean, one of the two must be more likely. I'm not saying that one of them is necessarily correct, but the question is just what is more likely.
Well, could it be likely that we don't understand the stars like you think we do?
No.
Why?
Because we've gained so much data about them in the last, 90% or so, probably in the last 50, 60 years, about what they actually are. No, we actually know what they are.
So we gain information on the stars, therefore we know everything about the stars.
We know their position. We know the nucleophysical reactions that are happening in them. Yeah, we know lots of stuff about the stars.
So we know about the stars, therefore we know everything about the stars.
No, that's not what I'm saying. I'm saying we know enough.
What are you saying?
I'm saying we know enough about them to determine where they are. And this is what is actually relevant for the geometry.
Not necessarily.
Yes, this is. I mean, the stars could be LED lights floating in that distance. If they still had the same positions, we still could use them to determine the shape of the planet.
But here's the issue. Appearance matters, Geo. Appearance matters. And if appearance matters, then that basically just throws off your whole argument, because you might think that this, like for example, you guys say that the sun is 400 times bigger than the moon, but it appears the same size as the moon because it's just further away.
Yes. You realize that the apparent size of the sun and the apparent size of the moon changes over time, right?
Yeah, after the energy. Yeah.
Well, yeah, all right. So you understand the geometry behind that.
Yeah, I get that. Okay, listen, I understand I just feel that you guys keep asserting it's impossible, and I think that's just be intellectually dishonest. If you're going to, the assertion you can make right now, and I will literally agree with you, is that this has not been explained on the flat Earth. I will concede. But if you're going to say it's impossible, that takes belief, because the moment you say it's impossible, I'm going to say prove it.
Yeah, and I am going a bit back to again to say that since you've started, or since you make that claim that it's possible without evidence, I'm justified in doing the opposite.
When did I say it's possible without evidence? When did I say that? I asked you the question. No, I asked you the question. I said, have you considered all the properties of the stars?
Yeah, and I said I have. And all we know about them, all we know about them points them to be pretty far away, and to be having the same physical properties that they think we have. For example, we can actually plug the light that is coming through them through a spectrograph and find out which elements they contain.
Okay, so my question to you.
Do you understand how stellar spectrography works?
Okay.
Do you understand that?
Yes.
All right, then please explain it so the audience knows.
So spectroscopy, basically, so we did this in chemistry class when I was in college. We got a tube, we put a certain concentration of, I think, phosphorus. I forgot the specific chemical.
I'm talking about.
And then we tested the. Hold on, let me just finish. Then we tested the absorbance of we tested the absorbance. I forgot what equation we used, but it was like absorbance and transmittance. Okay, I'm sorry, I can't remember. It's been about a year.
The way this works in stars is the following: when you take a look at different elements, like for example hydrogen, helium, lithium, beryllium, boron, and so on and so forth, and you shine light at them, at like vapor of them, gas of them, you will see that the individual elements absorb light in very specific wavelengths. Or the other way around, when you're taking that element, for example, sodium is a good example, sodium vapor, and you heat that up, you apply energy to it, they will start irradiating light of the same wavelengths. And by taking a look at the light that is coming from stars, we can find the different wavelengths of where the elements in the stars absorb them. So we can determine which elements each individual star contains. All right.
Sure. So basically, you're deducing the composition of the stars by what they emit, correct?
Correct.
So okay, hold on. Can I make one point? Can I make one point?
Sure.
A car emits exhaust. Therefore, a car is made out of this exhaust. That's basically what you're saying.
No, that's not correct.
How's that not correct?
No. We know that. For example, when you go to a car analogy, we know that the car emits CO2, nitrogen, water vapor, and a few other things. But we know about cars that they are made of different materials, right? With stars, when we take a look at stars, we know that they're actually gaseous. We can see that they are gaseous. For example, the sun. And we can see by the spectroscopy lights that there are actual lights, actual wavelengths that do not correspond to elements in their non-ionized forms. We can see that, for example, in the sun, there's a wavelength that corresponds to highly charged iron ions that have been stripped of a lot of their electrons. So from that, we can derive the temperatures and the conditions that are present in the stars.
So what I'm trying to say here is, how do we know stars just aren't converters? Like, what if they're just converting things, and we're just measuring what they converted? I don't. What they emit.
That is what they are.
Hold on.
No, but they don't emit it. The elements that we measure aren't like irradiated away. The only thing that is irradiated away is the photons.
Okay, but like my car example, emission only tells you so much. Emission only tells you so much. So I understand the logic behind deducing the composition of the stars. I get it, and honestly, it makes sense. But it only tells you so much. I also understand that just because a car emits exhaust doesn't mean it's made of exhaust. And yes, you're right. We do know the parts of the car, but we don't know the parts of the stars, because I don't think, have you flown to a star and seen it yourself and deduced that a star wasn't a car?
First of all, your analogy makes no sense. And second of all, we don't have to fly to them. For example, when you're saying that the stars are near, right? Flat earthers are saying that the stars are near, only a few thousand kilometers away.
Okay.
Right? And when you take a telescope and you zoom into it, you can see that it's practically a point source, meaning that the angular size is pretty small. Okay?
Okay, sure.
All right, that means that not only if the stars were near, not only the angular size would be small, but also the actual size. And when we try to run, like for example, fusion reactors, we quite easily run into problems when we try to scale this shit down. We can't run fusion reactors the size of the angular size that you would expect over that distance. We cannot do this. We know that the conditions for the fusion reactions to fire up need a certain temperature, obviously, but they also need a certain pressure from the outside, because you have to actually squeeze the hydrogen atoms so far together that they actually start fusing. And this is not something we can expect from an object that is only 6,000 kilometers away, because the outside pressure would simply not be high enough for it to be possible.
Yeah, so just by that explanation, you already are coming off with a lot of presuppositions that's going to really take us to the foundation of chemistry. And
so you're realizing you're talking to a chemistry major, right?
I have a minor in chemistry, so I can kind of talk with you on that. Now, mind you, I only took organic 1, 2, and I took quantitative analysis and a few UP courses.
All right. So first of all, what has this to do with chemistry? We are currently only talking about astrophysics.
Right, but I'm saying this is going to get us down. The presuppositions you mentioned are going to get us down to the foundations of chemistry, because you brought in some presuppositions about you're basically saying, well, how we understand the stars means that they're going to work a certain way by your.
I'm sorry. This is all astrophysics. Or nuclear physics. How's it called? Yeah, nuclear physics. Sure. This is not a chemistry case. We're not talking about chemistry. We're talking about plasma, and plasma chemistry doesn't happen. So what a chemist actually cares of is the electron shells around the atom. For all we know, for all chemists care, is that the core or the nucleus of the atom is an object with a certain charge and a certain mass. That's all a chemist cares of, except for NMR spectroscopy. But other than that, everything we've talked about so far is nuclear physics.
But isn't the foundation of chemistry the nuclear physics? Because how the basically structure determines function. So how the atom is set up in the nucleus that determines how it functions. Correct?
Yeah, the charge of the nucleus determines how it functions. But the actual characteristics of the of the nucleus don't care for chemists. Don't care. It doesn't care about them. Again, for all we would care, we have to know the spin of the nucleus. We have to know its mass and its charge. That's everything we have to know as a chemist.
The spin of the nucleus, the charge, and what? What else?
The spin, the charge, and the mass.
Okay. I don't disagree with that.
Right, you know what the spin is, right?
The spin of what?
Of a nucleus.
Like, are you asking for a quantity here? Do you want me to give you a specific number? Doesn't
No,
that depend on the element we're talking
just explain to me what it is.
So they're electron. Well, I know about the electron shells and stuff, but the actual spin of the nucleus. I mean, no, that's
let me just summarize this in one sentence. The spin of a nucleus is a quantum number that determines the magnetic characteristics of it. That's it.
Okay, so does it increase with speed?
What? No. Of course not. No, the spin of the nucleus is a function of what type of nucleus it is. For example, electrons have a spin as well. It's either plus or minus 1/2. And from knowing that we can determine, for example, how magnets work. Magnets are a direct result of electrons having spin.
Hold on. Are you saying the spin is constant? Is that what you're saying?
Yes, the spin is constant for each particle. And I think if you had chemistry 101, you should know this.
No, I've had chemistry.
I mean, this is literally one of the first things that you get taught in like the second or third lecture.
No, we'll see. Well, I was taught about the SPDF shells, and we had to use a periodic table to figure out the configuration of the outer electron shells.
Yeah, all right. And you know that the quantum numbers, one of the 4 most important quantum numbers to determine the electronic state of each atom is the spin. It's the last one, and it's either plus or minus 1/2.
I mean, I know what you're talking about. But that is introductory chemistry. But at the same time, like we focus more so on like intermolecular forces, like hydrogen bonding, London dipole forces, things like that. So that wasn't like so what you're telling me right now, I mean, like, it's something I glossed over. That's why I asked you that question. I mean, you didn't really have to say, "Oh, you should know this."
All right, let's just go back to this. We pretty much know what stars are, to a certain degree, obviously.
We know a lot of things about stars. Yes.
All right, and we also know that by their nature they can't be close.
From our understanding, sure.
All right, therefore the stars are far away. Therefore, the lights coming from the stars are roughly parallel. Therefore, since the light rays coming from each individual star are parallel, we can determine that the interpretation of the coordinate grids that I've shown, namely this. I'm currently sitting right on the equator. We have the northern celestial pole over here and the southern celestial pole over there. If I shut off the floor. First of all, let's shut off the atmosphere. And where's the floor? There we go. You can see that it's pretty much on 0. And on this side it's on 0. Since we know the stars are far away, we know this interpretation is correct. Therefore, the Earth is not a flat disk, but it is a sphere.
Oh, whoa! I disagree. I mean, so let's start from the first premise and let's work our way up.
All right. You already agreed that by their nature, stars can only be far away.
And explain that because
because basically for the nuclear fusion reaction to fire up, they have to have a certain pressure inside them, and therefore they need a certain size, and therefore since we know the angular size, they have to be that far away. That's the first thing.
Hold on. Do you agree with this? No, I have to look up nuclear fission.
Fusion, not fission.
Oh, thought you said fission. Hold on.
No, it's fusion.
Because I guess see, this is why I didn't want to go this deep, because I knew it was going to turn into this. Okay. Nuclear fusion. So what you're saying is, the sun's main sequence star is dust genetics is energy nuclear fusion of hydrogen, nuclear helium in its core. The sun fuses at 620 million metric tons. Okay, hold on. So how can we verify this?
By taking a look at smaller objects and finding out whether they start fusing.
When you say small objects, are you talking about like on the nuclear level?
No, on the nuclear level, no, not necessarily. You can start with like really small objects. For example, if you have only two hydrogen atoms interacting with each other, do they fuse? at room temperature, for example.
What would I use to measure this?
You would be searching for gamma radiation. Is it gamma radiation? Like the photon that is coming from there when they start fusing, because one of the two protons will become a neutron. Therefore, you have a charge that has to go somewhere, and you have a energy release that has to go somewhere. So yeah, you would be able to detect radiation coming from this.
Okay, no. Did you tell me the device I need to do this?
A spectrometer.
Okay, spectrometer.
I don't know which one exactly. If you want to talk about nuclear fission, I recommend talking to my friend Hector. He is actually a physicist.
Okay, well, listen. If we're gonna get now I have to look up stuff and look up prices and stuff, and it's just gonna be like messy. All right, so let's just deviate from here. Let's just deviate from here. Can we at least agree that what you just said, everything you just said, is predicated on our understanding of the atom? Can we agree on that?
And if you're now saying we're not understanding enough about the atom, I could give you about 20 hours of lectures of chemistry, and that's just the introduction.
Well, you can't tell me what an atom looks like. Nobody really knows what an atom looks like.
Oh, I have seen atoms. It's called an STM microscope.
Well, nobody's seen that, and we just deduce their structure by their indirect effects.
No, you can literally see atoms with a certain microscope, and it's called an STM.
Show me an atom. Then. Let's see what atom. Just see an atom.
STM microscopy.
Because I actually saw a recent lecture that even said that nobody's ever seen.
Do you know how STM microscopy works?
STM microscopy.
It's called scanning tunneling microscopy.
Scanning tunneling microscopy. Okay, and how does it work?
All right. Basically, it works similar to an old record player. You have a tip, and you're taking the tip and drag it across a metal surface that you want to scan. And that metal surface is connected with the tip via a circuit. And you're applying a voltage. And depending on the distance between the tip and the surface that you want to scan, there will be a different current that is running through the system, through the circuit. And you can measure that. And from measuring the actual strength or the actual size of that current, we can determine the distance between the two. And we can determine various chemical properties of the surface. And let me just show you a picture of it. So when you just Google STM microscopy, you will get these type of pictures. And those actual dots are actually the individual surface atoms.
Hold on, are you sharing those pictures? Or are you?
I should be, yes.
I'll just see the stellarium right now.
Oh, wait, then just switch off sharing. Monitor 1, can you see it now?
Okay, now I see your face rotating in circles. See a black screen presenting to everyone.
Maybe I have to shut off a stellarium.
Yeah, maybe.
All right. Is it better? Apparently.
I should be sharing. It might be lagging a little bit, but I'm still seeing a black screen.
Are you looking?
Maybe the side check can see it. Okay, I see it. Yes.
All right. So these are STM pictures.
Okay, and so these are scanning tunneling microscope. Okay, go ahead. All
right, so on every single, on the X and then the Y axis, you have like distances. So you see this this part of that surface that was scanned is about 5 nanometers in size in one direction, 5 nanometers in size in the other one. And these individual light and dark parts actually mark the positions of the atoms. So yeah, you can see the atoms directly using a microscope.
Well, you just described it measuring its indirect effects, so.
No, you're actually measuring directly the size. If you know the size of that bump, you know the size of the atom, for example.
So this is what an atom looks like?
What it looks like? No, it's like what you do with the STM is you actually look at the positions of the atoms on the surface. If you know, do you understand the difference?
It honestly sounds like you're describing indirect effects. Look.
No, this is a direct effect of the positions of the individual atoms on the surface.
So okay, so this is what an atom looks like.
No, that's not what I'm saying.
Okay, so where is a picture of the atom?
There is one right there.
So this is what atom looks like.
No, this isn't. This is what the individual atoms in relation to each other look like. You can see the positions of the atoms. If you're saying, how does one atom look like? There is no logical answer. Because when you're sending a photon to an atom, you will get a weird result out of it. You
so nobody.
See,
so no one has seen an atom, then, correct?
What?
So my assertion was right. No one has seen an atom.
Then no, that's not correct. For example, do you know? I have to look up the English word. This is another example of simple chemistry. I just don't know the English word. Ah, yeah. Do you know what a flame test is?
A flame test?
A flame test.
Is that like when you burn something and you see what color it is or something?
Yes. You can determine what ions you find in salts by burning them in a Bunsen burner and then checking out the color of the flame. Right. So in this case, it's literally the, for example, potassium ions tend to have a very like purple, light purple, pinkish type of color. And in this case, it's literally the photons coming off the atoms. So in this case, you could say that these atoms look purple when at the temperature.
Okay, so
because they're irradiating a photon of that individual wavelength and therefore color.
Okay, so it seems to me that you're saying that we know enough about stars to determine their distance.
Yes.
Okay.
All right.
Well, what I'm going to have to do is, you know, obviously you said you're a chemistry major, you said?
I'm currently doing my master's in chemistry, which will be shortly followed with my PhD.
Oh, cool. Awesome. I'm just going to have to look into get deeper than I want to get in this, and I don't really want to get that deep. So do you have like any lectures or any professors you recommend me look up?
On stars? No. But if you want to take a look at like flame tests, I recommend basic.
Well, yeah, I know about flame tests. I'm just talking about like things that can just about like that STEM. Like that's the first time I've seen that. And so, is there any
it's called STM. Look for a book called, oh, for fuck's sake. STM and AFM by. I'll send you the link later if you want.
Okay, yeah, definitely.
There's like a standard book for it. I don't know if it's available in English though. I just have the German version. At least I had it in my hands. I used it for my bachelor's thesis. I haven't bought it though. I should have. It was a nice one.
So let me try to make sure we're on the same page here. So you're not necessarily asserting that we know everything about the stars. You're saying that we know enough about the stars to determine how far they are. Correct?
Yes. I mean, we know pretty much. I think you underestimate what we actually know about them. Like we can, for example, determine only by their color which type of nuclear fusion reaction is going in there. That's one thing. But just to simplify it down enough, yeah, we know enough about them to determine that they are far away.
Well, just from my understanding is you can only know so much about emission, but now you're talking about nuclear reactions and stuff with something I have to look into. So I don't want to just speak about something I don't know about. So I'm going to, I know people hate when I say this, I'm going to look into what you just said. And when you send me that link, I'll look at that. And because honestly, I want the truth, you know. And if maybe you have to go this deep to get the truth, well, you might have to go that deep. So I'll look into it. But now that I let you go, I think it's my turn to go. Let me bring up this video. I'm gonna share a link.
Well, we haven't finished the argument though. We are now at step 1 of 5 or so.
Well, okay. It's kind of pointless to continue because now you're speaking about something about nuclear.
I mean, you can for now just assume the stars are far away. If you want to check that and falsify me in this, be invited. But my argument isn't over.
Okay, we'll keep going.
All right. So since we know the stars are far away, it's reasonable to assume that the light coming off of each individual star is parallel. Like there's no big angle between 2 light rays or 2 photons the path of two photons coming from the same star, right?
Okay, hold on. So, and this is all based off just their emission, correct?
No. Well, this part of the argument is basically, since we've established before that they are far away. Okay.
But well, to establish that it's based off their emission, correct? Because I mean, we're not going to the stars; we're just calculating what they emit, correct?
We're not calculating it; we are measuring it directly.
Okay, we're measuring what they directly emit, correct?
Yes, and we can measure directly which elements they contain.
And then, so we're measuring what they're emitting, and then we're postulating what they're made out of.
No.
What?
No, since we know what first of all, the emission lines that we get from the stars do not mean that they emit that individual element. It just means that this element is found in that star. Do you understand the difference there? Because, for example, a hydrogen atom, or let's take something heavier, like a silicon atom that happens to be in that star, is hit by a photon, and then it irradiates that photon out again. So then it has a certain wavelength. And that is something we get up. That does not mean that that silicon atom is going to leave or go away from that star.
And this is all determined by emission, correct?
Yeah, pretty much.
Well, there we go. Okay, so we really can't even draw that conclusion.
No. You conceded before that we can assume, or you conceded before that we can say that they are far away based on the knowledge that I presented.
See,
so now it's time for the second point.
You were talking about nuclear stuff, which something I don't know about. So what you're saying?
You admit that you're ignorant about anything regarding the nature of the stars.
Say what? I admit that I don't know a lot about the stars. I'll admit that, but I'm just trying to see what you know about the stars so I can understand where you're coming from, because that's what I care about. I want to understand.
Yeah, I mean, I already told you, and I said from the knowledge that I have and pretty much every single other scientist has, we know that they have to be far away.
Okay, but why wouldn't you just admit that you're drawing this conclusion based off their emission?
I already did tell you that we get lots of information from their emission.
Okay.
All right. So the next.
Okay.
So
the
next point in that line, we established that the stars are far away, right? I mean, I established it. You're not so sure about it because you're ignorant in the subject, but whatever. I'm now establishing that the stars are far away. Therefore, let's just take a look at one individual star, like, for example, Sirius. It's called Sirius in English too, probably. All right?
Yes.
All right. So when we actually zoom into stars using telescopes, we see that they're even smaller than this one. The only reason that we can see this star as a circle now is like the program itself. But the better of a telescope you are, the smaller this one will appear. Okay?
Okay.
So since the stars are so small, we can practically determine that the light coming from them is roughly parallel. Like every single photon coming from them is approximately parallel. The angle between two individual photons radiating away is pretty much the same for them. So there's no big spray in angles between the two.
Sure.
All right. That means that, for example, light, at least outside of the atmosphere, doesn't like, or that implies that the light outside the atmosphere doesn't like bend in different directions. The light rays are approximately parallel. Okay?
Okay.
Okay. That means that on every single position on the planet, the light is coming from the same direction.
So there can't be refraction and like photon pollution?
Photon what?
Like light pollution? Like
yes. I mean, the angle that they can be diverted off of is pretty small. Over the horizon, you can see it actually happening. I can actually demonstrate this. where is it? First off, switch off the ground. There we go. No, that's the wrong coordinate grid. There we go. So 0 degrees plus minus 0 degrees. This is the horizon right there. Okay. So let's take a look at that star, that one over there. The atmosphere is currently switched on. And when I switch it off, you see that the star is actually at a little bit of different position. I think it is probably this one. Let me check. No, it's not this one. Where is it? That one. So you see about half a degree or so of refraction. That is directly over the horizon. And we take a look at the star that is pretty much directly overhead, like this one. We switch on and off the atmosphere, you see that the star is approximately at the same position.
So you're saying it's insignificant, basically?
Yes, I'm saying that when you're not taking a look at the star that is directly at the horizon, the refraction in the atmosphere is insignificant.
Okay.
Okay. So what I'm going to do now is I'm going to open a program called GeoGebra. It's a geometry program. So I can show this to you.
It almost sounds like your name.
So let's just take a sphere and let's make this approximately 6.3 in diameter. So this is in this unit is in thousands of kilometers. So from here to here, it would be 1,000 kilometers. Okay.
Sure.
And let's have one point on the northern celestial pole. That would be here. And one on at like 45. I'm just eyeballing this, okay? Like okay. 45 degrees or so north. Let me just also draw in a... Oh, sorry. There we go. Just draw in a line that represents the x-axis. Not that one. Sorry. There we go. This line represents the x-axis. So now let's take a look at light coming from the northern star. We know that on the northern pole, it's directly overhead, right?
Sure.
All right, so this line, this black line here, let me just draw it in another color. If the program lets me, let's just do this in red. This light ray here represents light coming from the northern star. Oh, for fuck's sake, from the northern star. All right, so in the argument before, we established that if the stars are far away, the light is roughly going to be parallel, right?
Yeah, sure.
All right, so that means I have a tool here that can practically draw parallel lines. At least I have it somewhere. Where is it? There it is, parallel lines. How does this work? Choose a point and then, okay. So now we're taking a look at this observer here at the position D. And as said, he's not at the northern celestial pole. He's at approximately, well, somewhere between maybe 35 and 45 degrees, somewhere there. All right.
Okay.
So I've now drawn a line in. That is parallel to the first one. That describes a photon coming from the pole star to the observer D.
Hold on. What position? Like, okay, so I'm kind of confused on the position. So it's like, is observer...
So the observer C is at the northern pole, and the observer D is pretty much where I am, at approximately somewhere between 35 and 45 degrees. Well, I'm at 49 degrees, but whatever.
Okay. You see where the A point is at?
Yes, that's the center of the planet.
Would he see... Oh, D's on the outer edge of the planet. Okay.
Yeah, forget the center. This is just, I just choose the middle of it for geometrical reasons, so that it's easier to get the right numbers.
Okay, hold on. Would C see the stars as well?
C will see this. Yeah, C will see some stars, but not all of them. That's the point I'm trying to make. Okay. So we can see that C can see the pole star and D can see the pole star, right?
Right.
Okay. By the way, obviously these don't continue through the planet for obvious reasons. Actually, let me do the following thing. Fill it with, no. There we go. Red, no. What the heck? Oh, there's something wrong with it. Forget it. I just wanted to fill this circle, but for some reason it doesn't work. Whatever. So now, since we know those two lines are parallel and we know the position of D, we can actually determine the angle of the incoming light ray as seen from position D. The way this will work is, first of all, I'm going to determine the actual angle. So this guy is at 40.18 degrees north. Okay. So you see that I just drew that angle in there. Okay.
Sure.
And now let's find out where D's horizon is. Obviously, the horizon is perpendicular to the line directed to the center of the planet. That's how the horizon is defined. So there's a tool here, which I can use to draw this in. So this line here, that I will mark blue, represents the horizon of that guy. The last thing we need to do is actually find out that angle, because that angle will be the angle of the pole star over his horizon, over D's horizon. So let me just draw in 2 more points on those 2 lines so I can fill in the angle. And as you can see, this angle 40.18 degrees is identical to that angle, 40.18 degrees. So when I showed you in Celestia that the position of the pole star or the celestial pole over the horizon, that angle is identical to the latitude of the observer, this is a direct consequence of the geometry of the planet being a sphere.
Cool.
All right. And the funny thing is, we can determine from which position on you can't see the pole star anymore. But when you take a look at E, observer E, this guy is standing on the equator, right?
Mm-hmm.
So let me just draw in for this guy that line. So color this again. So the red line is the line or the way of the light that reaches the observer E on the pole star, on the equator, right? From the pole star to the equator. And as you can see, this is not directly on the. Just ignore that it's directly on the sphere. This just let me do this correctly if I'm already doing this. For fuck's sake. So there's a perpendicular line. No, that one. That one. No. For some reason, it doesn't want to work today. All right, then let me just try to do this manually. So this observer is now called J. And let me draw in his parallel line. There we go. Color this red. So this is the line coming from the pole star to the observer on the equator. For some reason the program doesn't like me today. I don't know why. Okay, so we can now say that obviously the light from the pole star can't reach anything anymore that is more south than the equator. Right?
Unless refraction is really, really big. But yeah.
All right, what about somebody on the South Pole? Can he see the northern star?
No.
All right, yeah, because the entire planet is in his way. And let's just take a look at another star from which the light is coming in a different direction, okay? And let's just say that star is directly overhead of the observer D.
Okay.
All right, so this observer D sees the star. Let's mark this star in green. Directly overhead. Okay. Okay, can the guy on position J see that star?
Can the guy on position J see the green star?
Yes.
Well, if his line of sight intersects with the green line, yes.
All right, so you're saying yes, and yeah, obviously that's correct. When you take a look at this, this was green. Yes, it overhead. And again, you can calculate the angles between the two. They will also, the difference between the angles will turn out to be 41.18 degrees. Yeah. And we can do this for every single star. We can see that there will be a point on the southern hemisphere where you can't no longer see the that star. You can't no longer see that star because the planet is in the way, right? There will be a point somewhere around here where you can no longer see the star. I tried to draw this into this, but I don't know if this will work.
Right.
So this would be, I'm just eyeballing this, approximately there. Okay.
Okay.
So all the range where that star can be seen from would be, this is the one side where the star can be seen from, right? Just properties green. And so this guy has that star directly over the horizon. Now, when we yeah, there we go. Let's draw just one line from this observer K, who is in the southern hemisphere, to the center of the planet. And when we extrapolate that line, we will end up in this other position over here. Now, can this guy over here see that star?
Can he see the green star?
Yes, the green one, obviously.
Does light shine in all directions?
Established that the lines, that the light coming from the star is approximately parallel.
I know, but does light? So let's say I have a circle, right? Yeah. Does light shine perpendicular to the surface of the light source?
Yes.
So there wouldn't be a line to reach the guy?
No.
Why not?
When we take a look at this, I said the line of the star is approximately parallel because it's far away. Therefore, this guy also is able to see it on the other side of the planet, but only above his horizon. Like the angle between its horizon and that star is practically zero.
Wouldn't it be parallel in all directions, though?
Wouldn't it be parallel in all directions?
Yes.
I don't. What all direction? From where?
So let's say I have a let's say I have a circle, right?
Yeah.
Or I guess okay. So if light is shining perpendicular to the surface of a circle, isn't light shining in all directions?
You mean from the center of the circle to the surface? Well, here's the bottom line. Only half of the sphere, or in this case, since you're doing this in 2 dimensions, only half of that circle is able to see the star at any given point in time. Since the entire thing is rotating, one part of the sphere that at this position in time cannot see the star will be able to see at the other time. But no, actually, that's not the case. Wait, let me think. Yeah, since let's go for the pole star.
Okay.
Let's just say this thing is rotating from B to J. Like, which direction is pretty much irrelevant. But we can say that every single point north of B and J can see that pole star, right? And we can make predictions of when you take a random star coming in from with its light coming from another direction, like any random star, we can determine how much of the planet is going to be able to see that star. For example, we can say that this star cannot be seen south of this latitude. No point in this part of the circle will ever be able to see this. When this thing is rotating, for example, a point here will rotate on this side over here, they will be able to see it. But this part south of K, everything from here all the way around to approximately here will never be able to see that star. Never.
Okay, so let me try to illustrate what I'm trying to say here. Okay, let me screen share real quick.
Yeah, but could you please answer my question first? Do you understand why I'm saying that that part of the circle will never be able to see that green star?
Well, I don't agree with it. That's what I'm trying to illustrate.
Yeah, but do you understand it?
Do I understand where you're coming from?
Well, yeah, let's say this thing is rotating by this axis over here. So this is coming from here, then over there, and this is rotating backwards over there, if you understand what I mean. Imagine this entire thing being three-dimensional and a sphere. That means that if the star is stationary, no point between approximately here and approximately there on the circle, on the surface of the circle or the sphere, will ever be able to see that star. And the thing is, this is exactly what we find in reality. So only using a two-dimensional representation, we can determine what we should see on a spherical Earth. And this is what we do see.
Okay, can I go now?
Sure.
Okay. So let's see here. Let me get to my beautiful paint. All right. We're going to do a circle. Okay. Do you see the circle?
Yes.
Okay, so let's say light is traveling this way, perpendicular to the surface, correct?
Yes.
You agree?
Mm-hmm.
Does light also travel this way as well?
That depends on what kind of light source you have.
Let's say that this is a perfect ball. And this
okay,
is
so it's practically a light bulb.
Yes.
Okay.
So light is sorry. So light is traveling this way, it's traveling this, it's traveling perpendicular to the surface, correct?
All right.
Okay, so if we have a light source, let's say this is like make that pink. No, I'll make it blue. I'll make it blue. Oh, actually, I kind of like that better, but we'll go like that. We'll make this inside blue. Okay, so this is the star, right?
Yeah.
It's a billion, gazillion, quadrillion light years away, or however far you guys say this. Okay,
you should
so
maybe draw this by scale, because otherwise you will get problems.
Okay. Well, I don't have that thing you have, but let's just pretend this is just scale. This is a gajillion, bazillion miles. Okay, so we have light. You said light's going to travel parallel.
Yeah, this is a consequence of the stars being far away. I think this is what you misunderstand. Let me show this to you. I know exactly what you want to paint.
Let me just say one more thing. Okay, I'll let you go. Let me say one more thing. So if it's going to travel, this far and reach parallel, you know what I'm saying?
Well, no.
Wouldn't it also travel this far?
Yeah, sure.
And also travel this far?
Yeah.
Okay, so do you realize how big they say these stars are? Because actually,
yes,
this
I understand
ball.
That.
So if this ball is actually bigger than the ball that you just said, let's draw the scale like you say. Okay.
Yeah, let me draw this by scale. I can do it.
So now it's this big. Hold on, let me finish my point. Then that means that even people can see the stars, like basically if you're on the North and South Pole, you still should be able to see both stars.
Yeah, I can actually show you a two-scale model of the solar system in the sense of I have the Earth, the Moon, and the Sun at relative positions and relative sizes, at least somewhere. This might take some time to find it, but it's somewhere here. Should be. No, obviously not this one. Oh, fuck's sake, I accidentally closed the other one.
How do you stop screen sharing?
Oh, you don't. On the top left, there's a button with a monitor and a monitor with a green picture and a white arrow on it in the Google Hangouts thing.
Oh, okay, thank you.
All right, so
okay, back on you. Let's go.
Let me just find this. Not this one. I hope I still have this. This would be cool.
It's like another program or something?
It's the same program. It's just a file that I don't often use. I used it once in a hangout with Anthony. Should be somewhere. All right, then. No, I don't find it right now, so I'm going to draw it manually. So, new one. Let's draw the sun. Sun has a diameter of 1.3 million kilometers. So I'm going to this by a scale of 1 to 1,000. That means that this thing is here will be the center of the sun, okay?
Okay.
And then 1 point on the surface of the sun will be at 730,000 kilometers. So since I'm going by a factor of 1,000 and this thing is in kilometers, should be approximately there. And just check this. So sun diameter is, equatorial radius is 695,700 kilometers. Let's round that to 700,000, okay?
Okay.
So this is by 1,000 as a scaling factor. So there we have our sun. Okay? I'm just gonna draw this guy in yellow. So this is our sun. Now, the Earth is 1.5 million kilometers out.
Okay.
700 1 by 1,000. So this would be at 1,005, not 1,500. Completely derailed here. 700,000. So 1,000 is 1 million kilometers, thereby 150,000.
Okay, so
yeah,
right now we're
150.
Okay.
So the sun is, the Earth would be over here approximately.
A little bit to the right. Okay. Okay.
So you can already see how far actually the sun. Oh, that doesn't look. This doesn't look right. This would be 1 million.
Well, the sun is 93 million miles away, correct?
Yeah, I'm doing this in metric.
Oh, okay. Oh, sorry.
Yeah, and the Earth is 100. Yeah, I noticed my mistake. I'm at 15,000, not 150,000. That's the problem.
Oh, okay. Okay. Yeah. Cool.
So let's go a little bit further out.
Right.
150,000.
Okay.
Here's the Earth. And this, remember, this is the closest star that we have. Okay, let's just zoom out a little so I can show you the scale of this actually. So you have the sun over here, barely visible, and you have the Earth over here. That point in itself is bigger than the Earth is.
Okay, so now can you draw just like one, or okay, can you draw a parallel line from?
Yeah, what I'm gonna do is, first of all, let's draw the Earth. This will take some zooming.
Okay.
So we agree that this is 1 to 1,000. That means that the Earth is 6,300 kilometers in diameter. Therefore, I have to get a radius of about 6.3, which would place the surface of the planet approximately there. Right about there. Yeah. All right, so here we have the Earth. Oh, and when we're already doing this, we will need somebody on the, oh, that's not my intention. We will need somebody on the North Pole, and we will need somebody on the South Pole. Ah, for fuck's sake. Again, for some reason, the program doesn't like me today. So we got one guy here, and we got one guy over there. So E and F, remember, E and F are the approximate positions of the northern and southern pole. And as you can see, this entire thing is to scale.
Okay.
What we're gonna do now is we're gonna do the exact drawing that you had. So a bit of zooming, that will take some time. A little bit more zooming, because we will need two guys on the surface, or two positions on the surface of the sun as well. So we got one guy, or one position over here on the well, so to say, northern pole of the sun and one of the southern pole. Now I'm gonna draw in the lines that you would like to have. So we got one guy from, so E and F were the positions on the Earth. So we have G to E, we have G to F, we have H to E, and we have H to F. Those are the 4 lines that we need, and the 4 lines that you would have drawn in there as well. As you can see, they're slowly converging to the Earth. The Earth is right there. This will take a little bit of zooming. And they're going through the northern and southern pole. Now, do you see how parallel these lines actually are? I mean, you can still see the angle. It's about 1 degree or so, probably less. I mean, I could measure it, but it's pretty small. And this is the closest star we have. This is only one it's called astrometric unit, AU, 1 AU away. This is 8 light minutes. The next star, apart from the sun to the planet, is Proxima Centauri, and that is 4.5 light years away. So there's a factor of at least a few thousand, probably more of difference between, not difference, factor between this distance and the distance from the Earth to the next star. Can you imagine how small that angle is going to be?
Oh, it's going to be really small. Okay.
All right, so we can assume that the light rays are approximately parallel.
So here's my issue with that. So that makes sense if you're talking about looking at the sun, because like if you think about it, if you're looking at the sun, somebody directly on the North Pole and directly on the South Pole would see the same sun. But why does that not work for a distant star? Because these stars are bigger. So basically, the light that's reaching the North Pole should be reaching the South Pole.
No, that's not true. Stars come in different sizes. Most of them are actually smaller than the sun. The sun is above average in terms of size. Most stars are called red dwarfs, and they have approximately 15 to 35% the mass of the sun. That's the average size of a star.
Okay,
the sun is relatively large. Now, you're right in your point that there are stars that are bigger than the sun. But first of all, yeah, there are some of them are thousands of times bigger in terms of diameter than the sun, or hundreds of times at least. There's one that is like 10 astronomical units in radius, called VY. I don't remember it. I think it's VY Cephei. Whatever. The point is, can you imagine that the sun, a star that is 1,000 times bigger and 1,000 times farther away, will approximately yield the same angles between the light rays?
Can you just draw it?
Oh, for fuck's sake, this will take forever.
I mean, that scale is actually pretty fast. You just drew that sun pretty fast. Just draw one star.
Yeah, but it's a lot of zooming. All right, so let's do. I don't know the exact distance to that one, and I mean, I could do it, but it really serves no purpose. The point is that angle. If that star were 1,000 times further away, and we're talking about a massive star here, like the biggest one that we can observe. Even if it were just 1,000 times farther away than the sun, it would produce the same angles. But it's not 1,000 times farther away; it's billions of times further away.
Yeah.
So the angles that we're assuming are much smaller than the one that we get from the sun. Much smaller than that half of a degree. That obviously it's half of a degree. It's the diameter of the sun where the difference between the light rays can be. So yeah, we can assume that the light rays are parallel, and therefore the other arguments I made are valid.
Okay. So just like you said, the sun that you drew is interesting because it reached the top of the Earth and it reached the bottom of the Earth. Yeah. So I mean, let's say. Hold on, Geo, please. Sorry. So let's say something like Polaris. It's bigger, it's further away, but I mean, it should still reach one side of the Earth and the other side of the Earth.
No, the other one not.
What?
It can, as said, only one hemisphere of the planet can see that star at any given point in time. Right? Because the light can shine through the planet. I mean, in this drawing, first of all, I didn't account for the tilt of the planet. The positions E and F are not the poles; they are positions at 90 minus 23.67 or so degrees north/south. So the actual axis of the Earth would be a little bit tilted, like in this way. So the northern pole would be approximately there, and the southern pole approximately there. But yeah, the point that I'm making with this is the light rays that we can go by are parallel. So, for example, Polaris, I've just been informed in the chat, Polaris is 433.8 light years away. That is 27,043,979 units farther away than the sun. Can you imagine how small the angle is going to be?
But the light will still reach. The light will still reach. Like you pointed out.
The light rays will be parallel, which is what I demonstrated in this drawing. As you can see, from any particular star, the light rays here are parallel.
Can you zoom in to the Earth real quick? Because I want you to see my point. Or will that take too long?
In this one? Or in the other one?
On the model that you just drew, can you zoom into the Earth?
Yeah, I mean, I drew two drawings.
On the second one. The second
one, sure. Oh. I hope I didn't actually accidentally just close it. No, it's fine. Okay. So I'm zooming in. And just now we're starting the Earth to appear. So smaller.
Do you see how the light has reached E in F?
Yes.
Well, let's say a distant star bigger than the sun. Light will still reach E and it'll still reach F. Therefore, they should see the same stars, but we don't see the same stars.
Because they're coming from different directions.
Okay. Even if they come from different directions, the opposite pole will see the same star.
No.
Why?
For example, because I drew this in the other one.
I never even thought about that.
Yeah, in this drawing, the northern pole is at C, right? That means the Earth is rotating from B to J. And no matter how hard it is rotating, where it's in the rotation, which time of day it is, only the northern hemisphere, only from here to here, this half circle over here will be able to see the pole star, which is the source of the red light rays. So yeah, this is a pretty definitive proof that the Earth is a sphere.
No.
Oh yeah, it is.
I think the flat earthers in the chat probably understand what I'm saying. Just how you drew the sun, how it reached both of the poles. Well, the stars should reach both of the poles too, unless maybe
but
magic is stopping it.
No. Okay, let's just draw in. So, first of all, these two aren't the poles. We've established that because I didn't account for the tilt.
Right.
So the North Pole would be approximately there. And the southern pole would be approximately there. Let me just draw this into it. Fuck it. So I need one line, namely from here to here. Need one from here to approximately there. I know it's not accurate, but whatever. Actually, I don't need these two. I just have to find out the angle, definitive size. So this is clockwise. I think it's 23 degrees off. So this would be the northern pole. Let's go by 23 degrees. Oh, for fuck's sake. This is the southern pole. Okay. So the axis of the planet in this case, not that one. The axis of the planet is this one, and therefore the equator. Yeah. And therefore, this is the equator. These two lines are the equator.
Can you draw another point at, you see where D, can you draw another point opposite to D?
Wait a minute first. I'm gonna
use
colors to make this a little easier. So the green line is the axis of the planet, approximately, and therefore the blue line is the equator. Okay. All right. So now let's draw a line in for the pole star. So we know that Polaris is over the northern pole. So the light from Polaris would come from that direction, from over there. Okay. And now we know that it's 27 or so million, or let's just round this to 20 million times further away than the sun. And when we zoom in, we can see that like those two light rays are half a degree apart.
Question.
Sure.
Zoom in just a little bit more, please. Would light from Polaris reach point? Oh, you didn't even mark it.
This one,
that one, and the other one.
This one. Yeah, that's
that
just
one and the one opposite to it. Can you mark?
Yeah, I know what you mean. I have a tool for this. Where the fuck is it? There it is. So there we have one, and there we have the other. As you can see, when you were standing here, the light from Polaris would come directly from the direction where your horizon is. And this corresponds to reality. We can see that observers on the equator have the pole star directly on the horizon.
So both of those points that you just drew would see Polaris, correct?
Yeah, right over the horizon.
Cool. Now my question is, if you drew another star, let's say that's not whatever star, that's maybe near Polaris.
Yeah.
I wish you would label it because it's hard for me to.
Yeah, just say stop. This one.
I would say F1 and F2 because that's where you drew the lines at. I guess.
You mean this one and?
No, it's like F prime and.
Yeah, these are the ones on the this is the northern celestial the north pole of the planet. This is the south pole of the planet.
The ones that you just drew the parallel line to, F prime and F prime.
All right, these two. Okay.
So they would also see the same stars, correct?
They could see Polaris, yes, both of them.
Okay, so could they also see the let's say so that means that regardless of where you are, you're going to see the same stars as the opposite pole of you, correct?
This is not the opposite pole. This is another part of the equator. The blue line is the equator. For example, a guy in somewhere in Africa directly standing on the equator would be here, and some dude in Indonesia or Central America or somebody would be here.
Right.
Yeah, they will see the same one. I mean, obviously, one of the two is in broad daylight, so he can't see it because it's day. But yeah, it's still over his horizon, and it's at the position expected.
Okay. So let me get this straight. So let's say there is a star that is directly over us. Okay. And it's bigger than the Earth. It wouldn't point E. No. Okay, can you label a point that's directly opposing the point D so you can see my point? See what I'm trying to say here?
You mean there?
Yeah, right there. And we'll call that.
Let's just do this. I'm gonna eyeball this again. There we go. It actually does this accurately. It snaps onto the x-axis of the system, so that's nice.
Okay, so what point is that? What's it called? I. Okay.
So we would be on the southern hemisphere, right? Some approximately 30 degrees south. That would be in Australia, for example.
So D and I can see the same star. Granted, it's bigger than the Earth. No matter how. D and I can see the same star. Granted, it's bigger than the Earth.
D and I.
Yes.
Not when it's coming from this direction.
No, it's coming straight over E.
If it's coming E or D.
You see where E's at?
Yeah. All right. So yeah, when there's one coming straight from E, then I is gonna be able to see it,
and
but
D's
not all the time.
Too.
And yeah, D can see it, but not all the. D can see it all the time, but I can see it all the time. Do you understand why?
Why can't I and D both not see it all the time?
All right, we have to do this three-dimensionally, I think, but I'm gonna try. So think about the rotation. This thing rotates from F2 or from F1 to F2, right?
Right.
So that means that so this is at time 1 and this is at time 2. Now imagine what happens to point I when it rotates to the other side in 12 hours. So let's just draw in the line from that random star, okay? Let's start with this one. So this is the direction from where the light is coming. Okay? And you're right to say that right now I is able to see it.
Okay.
And you're also right that currently D is going to see it.
Okay.
Okay. But now let's take a look at what happens in 12 hours when I will wander to the other side of the planet. What's going to happen is, first of all, we have to draw in this parallel line to I. So this line here represents the latitude of I. And this line over here represents the latitude of D.
Mm-hmm.
So that means in 12 hours time, I is gonna be over here. The program doesn't like me again. For fuck's sake, doesn't this like me? I have no idea why this wants to do this. So there we go. I'm gonna eyeball this again, I'm sorry. All right, so 12 hours after that position on the plan on the planet was there over here, it will be over there. And therefore, when the light is coming from this side, this position will be no longer able to see this star, because it's blocked by the planet. It's in the shadow of the planet regarding that star.
But isn't that irrelevant because D and I can be at night at the same time?
D, no. So we're talking about two positions. We have D and we have I. Those are the questions.
They can't be at night at the same time. They cannot be at night at the same time.
No, they can't.
Wait. Hold on.
So wait, watch out. This position and this position are at the same time, right? Let's just say
you're going with the rotation. Okay, I see what you're saying.
Yes,
okay.
The rotation is relevant. And when it's rotating after 12 hours, that position over here will wander over there, and this position over here will wander over there. Now, this position can see the star at this time, and when it's over here, it can also see the star, since the light ray will be coming from approximately here to here. But when at this time, this position over here can barely see the star directly over the horizon. When it's here, it can't see the star anymore because it's blocked by the planet. Therefore, you expect to get, let me go to Stellarium again. You expect to see stars that dip over the horizon for a certain time, or under the horizon for a certain time as well. Let's just go by this one randomly. I hope I picked one that shows this behavior. Time. Let's increase the time by 1 hour. As you can see, it's below the horizon. Then there will be a point, we just extremely zoom out on this, when it will be visible again. There it is. So you can see there are stars that dip below the horizon for certain times. And that is only dependent on where the star is in the sky and where you are on the planet, as shown by this demonstration, by this drawing. So yeah, it's perfectly explainable by the spherical Earth.
You either pointed out a huge issue or had a great explanation. I'm trying to visualize it right now, but hold on, give me time, because it's almost like.
So this is something that flat earthers try to ignore.
I'm not ignoring it. No.
You simply don't appear to have known about this. But whenever I'm talking with a flat earther who knows about this, they try to avoid that subject like a plague, because this is a geometrical fact that you can't escape.
So let's say there was so you know how you drew the sun in?
Yep.
Okay.
So I can theoretically draw in the other stars as well, but when we zoom in, like let's just say I would replace for this star that is coming from the red side, or this red star. We would zoom in and we would see the angle between the two light rays, and it would still be infinitesimal small. We could zoom in all day and we wouldn't see any difference between the drawing like it is now. Even if the star is 1,000 times bigger than the sun, when it's millions of times further away, the angle will be much smaller than the one that we see from the sun. So yeah, there's no point in modifying this drawing.
Okay, so let's say.
By the way, do you want the drawing? I can save it and send it to you.
Yeah, I guess I got to get that program too, huh?
Yeah. It's a.
What's it called?
It's called GeoGebra, GeoGebra. It's a geometry program. Usually teachers use this to teach geometry to children. So I think it's quite practical to use it for flat earthers. Actually,
I'm trying. It's hard for me to. I'm trying to articulate. Oh, is this a? Okay, I think I found it.
So let's just save this as sun stars 2, and the other one. Let me save the other one as well, even though it's practically the same drawing. This was PTV stars -1. There we go. Both are saved. I think I can close the first one since we can work with the second one as well.
Okay.
So yeah, this is a geometrical fact that flat earthers ignore, and which simply can't be explained by a flat surface. It's impossible.
It's a way. Geo, come on now. Come on now. We just got through this. We just got through this, man. Don't.
If you're only going by geometry,
say it's not been explained. Say it has not been explained.
No, I'm sorry. If you're assuming that refraction is insignificant, which it apparently is, then it's impossible.
This is
because you will fuck up angles. You will get problems with the apparent angles of the stars when you're over a flat surface.
So okay. Well, if you're gonna, so are you gonna stand by that assertion that it's impossible?
Yes.
All right, prove it.
I already told you. Well, do you want to simulate this on a flat surface, maybe?
Well, hold on. You see, when you make that assertion, by proxy, you're saying that the Earth is not flat, because if the Earth is flat, then we are seeing it right before our eyes. So go ahead and prove to me that the Earth is not flat.
No, we're working the other way around here.
Well, then that's just circular reasoning.
Okay. Let's do this. So now we're going by a flat Earth, okay? And we know that the distance between the equator and the poles is approximately 10,000 kilometers. So we're going by a zoom factor of 1,000. So now here, so A would be, let's say, the northern pole, and B would be the southern pole. Here in the middle, this would be the equator. Okay. Actually, let's do this a little bit other way. I'm not going by size. I'm going by angle. So by the factor of 10. So at 90 degrees latitude, because this will be easier to do. 90 degrees and 90 degrees. This is just easier for me to explain this. So this is now our flat surface. I'm gonna give it a different color as well. All right, let's assume that there's a star directly over the equator. How far do you want that star to be?
I don't know. That's on you. You're the one trying to model.
All right. So let's just say the stars are infinitely far away. And let's just assume again the stars are infinitely far away, okay?
Sure.
And we have a star that comes in 90 degrees. Let's just start with the northern star, okay? The how is it called? Polaris. Polaris is 90 degrees overhead on the northern pole, right? B is the North Pole, okay? And this now red line would be the light coming from the North Pole. Now, when we assume the star is far away and therefore the light rays are parallel, then we would expect. I hate it when it does this. We would assume, or we would get the result that the light.
Wait, hold on.
Yeah.
You said if we assume.
Yeah, I mean the angles
will. No. You're gonna prove it. We can't make any assumptions. Come on.
I'm playing devil's advocate here. I'm trying to find out what matches best for your model.
Well, then that's the issue. You can say it hasn't been explained, but if you're trying to prove it, you can't. Well, if we just take this assumption, then it doesn't work. Well, maybe that assumption's wrong.
I'm sorry, but I asked you where you wanted the stars to be.
Well,
you didn't give me any answer, so I'm going by one example.
Well, if you know the flat Earth is not right, then you should be able to model it since
yes,
you know.
That's what I'm doing right now. So again,
hold on. It's possible your model is wrong. I mean, you already mentioned assumptions.
I already told you. Let's go by the assumption for this one time that the light.
No, we can't because you said you're going to prove it. You're going to prove it. I'm
going to show you that how much you vary the distance to the stars, you will always run into geometrical problems.
Based on your assumption. So you didn't
No.
prove it.
No. I'm going to go through various examples on why this is impossible.
Are you considering all the examples?
I'm going to consider some examples.
So you don't have proof. You just have some examples that you know don't work.
I'm going to go through some examples with the extreme cases on the end. In this case, we say that the stars are so far away that we can assume that the light rays are parallel. What I'm going to do next is pull the stars a little bit closer and show that you will run into geometrical problems there as well.
Question. Are you going to consider all examples?
I cannot. I mean.
Okay, so you can't make the assertion. It just hasn't been explained yet.
I can show.
I'll save you a bunch of time if you just say.
Let me just do this. Saying that the light rays are parallel, we would expect that if this.
I don't agree they're parallel.
Hey, I agree that they wouldn't be parallel on this flat Earth. This model here that I'm drawing now makes no sense at all. But I'm gonna show that all other.
I don't agree with your model.
Hello. Don't interrupt me. I'm going to show that all flat Earth models, no matter how far or how close the stars are, will not work. That's what I'm going to do.
Oh, so you have all flat Earth models.
Let me just do this.
Wait, no. You just said I'm gonna show how all flat Earth models don't work.
No,
so you have all flat Earth models.
This was a quote mine. I said all flat Earth models are wrong.
So you have all flat Earth models.
Again, You did it again. Let me make my point. What I said was I'm going to vary the distance to the stars, and I'm gonna show that every distance that I'm gonna show will run into geometrical problems. That's what I'm gonna do.
So is it possible that you're modeling it wrong?
No.
Okay, prove it.
Yeah, that's what I'm gonna do if you would let me.
No. You just you're modeling it right now, okay?
Yes, that's what I want to do for 5 minutes. Is it possible
that you're modeling? Is it possible that you're modeling it wrong?
No, it is not.
So you know everything about the stars.
Oh, for fuck's sake! You want me to model this, right? Then let me model this.
But you don't know how to model it. So maybe you're just modeling. You're just attacking a straw man. You made the assumptions. I mean, you made the assertion. So prove it. And this is what you think.
I want to, but you keep interrupting me.
Gio, all you have to say, because you keep making assertions. I'm not gonna let you get away with your assertions. If you're gonna make assertion, prove it.
I'm gonna show you.
If you cannot prove the assertion, Gio, you're gonna have a hard time proving a negative. Because when you say it's impossible, you're gonna have a hard time proving that. Just say it hasn't been explained yet.
I will show it to you if you would let me.
So you have all flat Earth models considered. Because by proxy, that's what you're saying.
Hey, I'm gonna show this to you, and if you keep interrupting me, I'll just kick you.
Well, because you're just speaking nonsense. You're making
we've been talking for 5 minutes now without me actually being able to do anything.
Then take back your assertion. Because you're just attacking a straw man. You don't even know if you're modeling it right.
That's why I'm saying I'm not doing just one model. I'm going to do a series of them and show that everyone is wrong.
So you have all models.
I have the extreme cases, and when those are wrong, the case.
All models. Yes,
again, you did it again. Don't do it again.
Do you have all models? Yes or no?
No, but
okay, there we go. Don't even make this point. Don't even make this point. This point's irrelevant. You don't have all the models. There you go.
Fuck's sake. Do you want me to try to model your flat Earth?
No, I don't.
So you don't want me to show that you're wrong?
No, because guess what? You're just attacking a straw man. You're just asserting this.
I'm not attacking a straw man.
No, I'm asserting a model and you're attacking it.
All right.
Do you not realize this?
I give you one more possibility. I'm going to explain this one more time. I'm going to do various attempts on modeling this. This one that I'm showing right now with the red lines assumes that the stars are infinitely far away. What I'm then going to do is draw the stars closer to see if we run into geometrical problems then as well. When we can say that when the stars is, for example, directly here and there's something wrong with the model, and for example, when the stars is when one star is here and we run into a model, then we can assume that all of them in between are also false.
All right, now can I respond to that?
Yes,
it's my turn because I don't. Okay, so what you're about to do, you asserted that on a flat Earth this is impossible, yet you don't even have the model. You're just making up a model. You're just making up a model.
That's not correct.
Okay, how do you know your model's correct?
Let me tell this again. What is again the standard hypothesis regarding flat earthers? Most of them are going by the AE map, right? Like 95% of them.
I don't agree with the AE map. So you're attacking, again, you're just attacking a model to what you pick. You're attacking a straw man.
All right, then you tell me where the stars are. And then we're going to check this.
The stars are above us.
Where?
They're above us. I mean, do you not know what
distance?
Above us.
Direction. Where?
How far they are?
Yeah.
I'm not sure. I don't have a model yet.
All right, then why, if you have none, why can't we just check if some flat Earth models are wrong? Why is that problematic for you?
Because you just asserted it's impossible on a flat Earth, which means
I will show you.
No. By proxy, if you assert that it's impossible on a flat Earth, by proxy, you're saying that you have the model of a flat Earth and you're about to debunk it. You don't even have the model of flat Earth. You're just going off the top of your head.
That's not correct.
So how do you know this is a model of flat Earth? How do you know?
Because most flat earthers use this.
Well, maybe they're using the wrong model. Most flat earthers will admit we do not have a model. But you're about to attack a model and say this proves it doesn't work on a flat Earth. It might not work on this granted model that you're using, but that does not mean it's impossible on a flat Earth. This is just simple philosophy.
What I'm saying is whenever you're trying to model the flat Earth in some way, you're gonna run into geometrical problems, and I can show this.
That does, okay. So no, based on your understanding.
No.
This is based. Oh, it's not based on your understanding.
No, this is based on geometry.
No, is it based on your understanding though?
My understanding on geometry, yes.
Okay, so is it possible that you just haven't considered a variable that makes it all work?
No.
Oh, how do you know?
Because we can try various examples, like extreme examples on
these various examples.
Again,
examples.
Sorry. Hey,
don't do it again. Examples
don't interrupt mid-sentence. Don't interrupt in mid-sentence.
Does various examples include all examples? Answer my question. Does various examples include all examples? Exactly. You can't make that assertion because you can't.
No, I'm sorry. This is your last chance. If you don't let me speak, I'm gonna kick you instantly. Again,
I don't care because you're making assertions. You're not proving it. I don't care.
Let me try to explain this one last time. This is your last chance. Now, when we take a look at various examples, we start with the extreme values. For example, the stars being right in front of your face and the stars being infinitely far away. And then we will run into geometrical problems. That is self-evident. And then we try to position the stars at different positions and check whether we will run into geometrical problems as well. So what I just did, demonstrated by the red lines, is that if any star were infinitely far away, we would expect, in this case, the North Pole star to be visible at the South Pole as well. What I'm going to do next, I'm going to draw the North Star a little bit closer and then check where the on which angle it should be visible from the South Pole. That's what I'm going to do. We're going to check various positions of stars and check and look whether we will run into geometrical problems. And this is very easy.
Can I talk now, or?
Yes.
If we run into geometrical issues, perhaps there's some variables we aren't considering. But like you just made it. But you just made the assertion that no, you made the assertion. So you have to explain how you know all the variables, because I didn't make the assertion. You did.
There are only two. There's
Okay,
position. There's position in terms of angle. Like there's 2 points in this diagram. There's the x value, which means in this from north to south where the star is. It could be outside or here somewhere as well, obviously. And there's the distance from the Earth's surface, or the flat Earth surface, which would be 0 over here and would go, well, over to the top. Those are the only two variables. As soon as we know those two, we can find out whether we will run into geometrical problems using only those two variables. And yeah,
so,
it's
okay,
a fact.
Okay. No, wait. Okay. So you're saying there's only two variables in a whole model of a flat Earth. There's only two variables.
Assuming that you're going by the AE map, yes.
So if I just told you I don't agree with the AE map, why are you going by the AE map?
Well, I asked you which map do you want, and you didn't answer, so I went by the most popular
because there isn't an official model, so you're just attacking the straw man. We understand we don't have a model. Do you not get that? I'm just saying it's intellectually dishonest to assert that it's impossible. You might say it's impossible. Hold on. Let me finish, yo. I'll let you talk. Now let me finish. Now you can assert that it's impossible on the AE projection. You can assert it's impossible on the square map projection. Whatever. Okay, cool. But you cannot assert that it's just impossible on the flat Earth altogether.
Yes, that is what I can do because I know how geometry works.
Oh my gosh, you cannot do that.
Yes, I can.
How do you not understand?
I can. Okay, fuck this. B and C are random points on the Earth. Okay, random points. They don't have necessarily
how do you know you modeled it right?
Because it's flat. If you're saying the Earth is flat, then therefore those two are on the x-axis.
Well, how do you know how do you know it has an end? How do you know it doesn't just keep going?
I'm saying they are random points. They could be in the middle of the Earth, just 1 kilometer apart, or they could be at the ends.
Okay, well, how do you know they're exactly at that position?
I say this is random. Forget the scale.
But you just said it's impossible, so surely you have the correct model to debunk, right?
I'm just currently eliminating two more variables, namely the distance between the two.
Do you have all the models of flat Earth?
No.
There you go. So you can't say it's impossible.
But yes, I can say it's impossible because it's geometrically impossible.
Based on your understanding of what the stars are.
No, but didn't you already agree that based on our understanding, we know what the stars are, and therefore we can assume that the
No, I did not. No.
Yes, you did that.
No, I didn't. What I said was, I said, hey, I need to look this over because you're talking about something about the nuclear. I'm talking about electron shells. I need to look this over. And I said, okay, but I'll play your game. I'll let you explain yourself. That doesn't mean I agree with you. I'm just trying to hear what you're saying. I'm trying to see it from your point of view, but you're being intellectually dishonest.
Therefore, you're saying that it's possible that the stars are closer, right? But you don't know where.
I don't know a lot about the stars, and I'll admit that.
All right, here's the point. Forget the scale. Completely forget the scale. Forget the numbers. Okay? You have just one random star somewhere. Okay? One random star. Okay? Can point B see that star?
I don't know.
Why not? Why shouldn't it be able to see that star?
Depends on the property of the star.
But it's there. It can
depends
only
on the property of the star.
How?
Depends on the property of the stars.
How?
Obviously, maybe different stars appear differently.
How differently? Do they switch their apparent positions?
No, hold on, no. You made the assertion. You prove it. No, you tell me. You made the assertion. You tell me.
They don't. That's the thing.
I don't agree with your assertion. Prove it.
Fuck's sake. All right.
This I'm saying, Gio. Gio, I understand that I'm making you frustrated, but this is what you're going to get when you make an intellectually dishonest statement. You cannot assert that it's impossible on a flat Earth. You have to say it has not been explained on a flat Earth. And I'll agree with you. Okay, we have some explaining to do. But if you're going to assert it's impossible, then you have to show me the model that you debunked. You have to show me every model that you debunked, because by proxy, you're saying it. We might be seeing it right before our eyes. So by proxy, you have to explain how I'm not seeing it right before my eyes.
Is there a direct line of sight between B and D?
Yes.
All right. Is there a direct line of sight between C and D?
Yes.
All right. Is there a direct line of sight between A and D?
Between A and D, yes.
All right. Can therefore all three positions C, D?
I don't know.
Of course they can. There's nothing blocking it.
The property depends on the property of how they see.
All right. Name one thing that doesn't follow this logic.
Let's say B has sight in which. Okay, listen. Let me talk. You asked me a question. Let me talk. Okay. Let's say B has a sight where his eyes converge a flat surface, and therefore it obstructs D. You
are making no sense whatsoever. His eyes, quote, his eyes are converging a flat surface, end quote. Right. What do you mean?
So basically, when he looks at a flat surface, it doesn't appear flat. It converges. So see what I'm saying? There's so many variables.
You're assuming that the light rays are not parallel. You're assuming that the light rays are not parallel. Or that the light rays are not straight. That they bend.
Okay, so listen. You said line of sight. Just because you have line of sight of something doesn't mean you can see it.
Yes, it does. That's exactly what line of sight means per definition.
Prove it.
Line of sight. Sight meaning being able to see something. Line of sight, therefore, meaning that there's a line between you and that object that is not crossing any other object, and therefore you are able to see that object.
Can a blind person see something that's in front of him? He has line of sight of something that's in front of him.
What again, please?
Can a blind person see what's in front of him?
No.
Oh, but what? He has line of sight.
Yeah, obviously we are assuming that there's light coming from that object and that the object can actually
so there's other variables we have to consider, but
no, there isn't. As soon as you're able to actually receive that signal, that's the point. For example, can you see radio waves?
Can I see radio waves? No.
Can you see? Okay, so you can't see radio waves. All right, let's say there's a big fat S antenna directly in front of you, like 100 meters in front of you, there's an antenna. Okay?
Okay.
Can that signal from that antenna reach you?
Can the signal from the antenna reach me?
Yeah, can it?
Sure.
All right, but you yourself are not able to detect it, right? Because you don't have an organ to detect radio waves.
Okay, so what's your point?
All right. But you can have a device that can detect the radio waves, like a smartphone, for example, or a radio, depending on what type of signal it is.
So you're saying that there's properties we have to consider of the organism observing it, huh?
No. That's exactly what I'm not saying.
Oh, so okay, let's say I do have properties to detect radio waves.
Yeah, all right. Therefore, you have line of sight to that radio wave tower, anyways. If you didn't have that organ, you just wouldn't be able to detect it.
But if I did, I could detect it.
We know that we can see stars, right?
Sure.
All right. And we know that when you stand on the equator, you can see the northern star, and you know that when we stand on the northern pole, you can also see the northern star.
Sure.
All right. Then, for example, the distance between, assuming it's a flat map, the distance between the star and you on the equator and the distance between the star and you on the pole would be different, right?
I don't know. You tell me. You're the one who have the model.
No, I'm asking you about your model.
No, my model.
Yeah,
what model? No. See, Gio. Now you're just being dishonest. What model have I brought to you?
None. That's the point.
So how are you gonna attack a model I haven't even brought to you? But you just said I have a model.
That's the thing. You have nothing. You have no evidence. You have no
but
idea
you
what
just said I had a model, Gio. You just said I did. So did you just lie?
Yes.
Oh, no. Wait, Gio. Wait, hold on. Did you just lie?
Are you a flat earther? Yes or no?
Yes.
Therefore, you have a model meaning the Earth is flat.
No. Just because you're flat earther doesn't mean you have a model. What type of logic are you using?
This is a model. You're going
just because you believe the Earth is flat does not mean you have a model. What? How is that so hard to understand?
A model is a simplification of a phenomenon or a physical reality, right? You simplify reality to a system that you can understand. As soon as you're saying you're a flat earther, therefore you think the Earth is flat, therefore you have a model. It's not complete.
No.
Hey, whoa! Again, this is your last chance. As soon as you say you're a flat earther. You have a model. It's not complete, but you have one.
I don't have a model.
Then why should we even discuss with you? The only thing that you can do is attack my model. But I can.
Personal preference. I mean, if you want somebody to have a model, that's just your personal preference. I can't help that. That's on you. But you just asserted that it's impossible. So where's your proof?
I already told you. You will always run.
Well, where's your proof? Come on.
All right. There we go. I'm done dealing with you. I'm sorry. I gave you various chances, but there's no point in talking to you anymore.
You're dishonest anyway, so I will leave my own.